Okay, welcome. So today I'm going to be talking about stromatolites and stromatolitic cherts of the Strelley Pool Formation, which is 3.4 billion years old in the Paleoarchean in Western Australia. Luckily, I don't have to go over too much about what a stromatolite is, because it seems like this crowd is pretty savvy about that. So the first goal of this project was what we're all trying to do, basically detect and characterize Paleoarchean habitats that we might be able to use for a proxy as other habitats on, planetary systems. The other goal was basically just to use in situ isotopic analysis of these cherts and quartz to better piece together the petrographic story of these rocks. So these are the three field areas that we used. You're looking at the Pilbara Craton again. I think you've actually seen this map a couple of times today. But we're in Western Australia, so we are in the northwestern corner. And the three sampling areas are Unconformity Ridge, and then there's a lot of data from the Trendle locality, and then Camel Creek. Quick note about this, the Pilbara Craton basically has all of these granitic complexes that are doming the sediments in the area. And so the Strelley Pool Formation is this red formation that is basically wrapping around those domes within the area. Okay, so here's a field shot of the Strelley Pool Formation. We're looking directly down one of the indurated chert ridges. The Strelley Pool Formation is bounded underneath by the Kuntaruna volcanics at around 3426 million years old. Above the Kuntaruna volcanics, we have an unconformity, so there's some erosion, an erosional period at that time. And then basically at the base of the Strelley Pool, we have these coarse clastic rocks, and that grades upward into finer siliciclastics, and then finally into cherts and stromatolitic layers towards the top. And then it's capped again by this coarse clastic interval. So going through those, here's the basal conglomerate of the Strelley Pool. You move up one and you're getting into a little bit finer sedimentary rocks, sandstones and cherts. Up a little further and you're into the bedded cherts. And then all of our favorites, stromatolites, is what you start to see after that. On the left, we have stromatolites that are dolomitic stromatolites, so there's actually some carbonaceous stromatolites preserved. And you can see that parts of these stromatolites have been silicified, so there's these little silicification fronts that come through and just partially replace. And some of you doing stromatolite research, I'd love to ask about this later. But and then anyway, on the left, or sorry, on your right, we have a completely silicified stromatolite, which is what we more often see in the Strelley Pool Formation. And then finally, we have basically druzy coliform quartz veins that cut across the Strelley Pool Formation, and sometimes these breccias up towards the top. So just a quick review on oxygen isotopes. I know most of you know what's going on with this, but we have a plot here showing temperature on the y-axis and delta 18 on the x-axis. And then these curves that you see are representing different values of water. And so meteoric water tends to be light. That's the evaporated water that we've talked about. Seawater tends to be at around 0 per mil. That comprises the Vienna Standard Mean Ocean Water Standard. And then finally, we have formation brines, which are just basically basinal brines that have undergone long interactions with rocks and have become isotopically heavier due to that. And so you can see that this is basically representing cherts forming at equilibrium with these waters. And so if you form a chert at equilibrium at 100 degrees Celsius with a water of, say, 0, then you should get a value of about 21, 22 per mil. Okay, so Precambrian cherts tend to be light over here in this 10 to 15 per mil, which means that they're either warmer or that the oceans were basically isotopically negative. Phanerozoic cherts form at these higher isotopic values, indicating probably cooler formation temperatures. So the reason I bring this up is there's this long-standing debate basically about what this curve through time means. So cherts in the past tend to be isotopically lighter, and then through time they become heavier. So scientists have offered basically three different mechanisms for this trend, this secular trend that we see through time. It is either due to oceans being lighter in the past, temperatures being warmer in the past, or just the fact that all of these rocks over here have sat around longer, so it's more likely that they're altered and have seen some hydrothermal activity, basically. The gray curve you see here is from Aubert and Chalcedon, and this is what they propose as the least altered cherts, because any post-meteoric or hydrothermal alteration should lower those isotopic values. So then we bring up some of our data, and we see that we've got this one group of data from the Trindle location that's significantly above that curve. So what does that mean? So then we start getting into the textures. Microquartz is basically one of the earliest textures, petrographic textures that I see. Then I see this mesoquartz, which is a slightly coarsened version of microquartz. Then we move into megaquartz, which is often found in veins, and then just throughout the sample. And then we have cavity megaquartz. Cavity megaquartz is this euhedral quartz that's growing into cavities and voids, like a geode in a way. Then there's detrital quartz and sandstone cements. And for any of you who have looked in a petrographic microscope, I just want to mention this is a thickly cut section. So that's why you're seeing high interference colors in quartz. And then finally, we see chalcedony, which is basically these banded radiating quartz. Okay, so that basically brings me to these two different groups that we see. We see an earlier, we see a lower delta 18 group and a higher delta 18 group. And the question was, what is this higher delta 18 group? And so with SIMS basically going in, we see that we really break this rule from Robert and Chalcedon with this higher delta 18 group. Basically, that higher delta 18 group is found in this cavity megaquartz, and then basically all of these coarser textures, which is telling us something petrographically. And then finally, these lower groups are found in these petrographically earlier textures and finer groups. So moving into this a little bit, out here you can see the groups that are basically, this is that druzy cavity quartz I talked about earlier. And then if we look at that with an SEM into one of the voids, then you can see the sort of geode-like texture I was describing. And then further, if I look at that with CL, which is cathodoluminescence, you see this really incredible zone texture in these. And these, in my mind, are clearly late. They're clearly growing in and coming in later. So one of the questions we had was, is this late druzy cavity megaquartz also present at depth? And so we checked into the, so we sampled from the, we sampled a core that was drilled through the Strelley Pool Formation. The Strelley Pool is in yellow, and then the drill core trace is in blue here. And then basically we found that the outcrop trend, we sampled a transect at the outcrop above the drill core, and then we sampled the drill core at depth. And then we compared them. And basically we found that we have sandstones and conglomerates at the base, once again, then moving up into those bedded cherts. This is all isotopically lighter because it's volcanic quartz, and so this is the actual detrital grains of quartz. And then we saw this step up, and we saw this step up right at the boundary between cherts and sandstones and conglomerates in both the samples at depth and on the surface. But you'll notice over here, the delta 18 does not get up to that 30 per mil that you saw earlier. Okay, so here's some of the in situ work we did. We found that the microquartz cements were right around 14 per mil. And then that the detrital quartz was right around this kind of 10 to 11, 12 per mil. This is an example of that. There's the 14 per mil quartz in the cements, and then the detrital quartz is right around 12. So what we found based on all of this is that we have these petrographically early textures that define this lower group. So these are the sandstones. This peak ends up being basically sandstone right here, that 14 per mil that I showed you earlier. And then these end up being those petrographically early microquartz from the Trindle locality stromatolitic cherts. And so that's, so once again, we can see that these early textures tend to be within that range of Precambrian cherts that we see. And then finally, the later textures tend to be in that 22 to 30 per mil range. So what we conclude from this is that we think there's an early silicification front, possibly hydrothermal, that comes through and forms these low delta 18 microcrystalline and earlier textures in the quartz. We think that late diagenesis or some sort of warm, heavy delta 18 fluid probably forms this Druzy cavity megaquartz. And this is a little difficult to constrain. We're not sure of the exact timing of this, just that it's late. It's petrographically late to the story. Drill core samples tend to be very similar to the samples at depth, indicating that at least in this area, we didn't have that presence of Druzy cavity megaquartz. We didn't have that high delta 18 group for one reason or another in that sampling area. And then finally, what we've concluded from this is at least within the Strelley Pool Formation, cherts are probably not a viable proxy for either the temperature of Paleoarchean seawater or the delta 18 of Paleoarchean seawater. And with that, I'll take any questions that you might have.
Oh, sorry, you're in my blind spot.
Thank you. Not knowing anything about the field, I have a stupid question. Is there any evidence about that you're experiencing a critical global warming in the history of Earth? I know it's irrelevant, but...
I think what we've found is actually that most of this is probably due, in my mind, to hydrothermal activity. If I were to give a single answer to why I think the trend, there's this secular trend in cherts through time, it could be that there's just increased hydrothermal activity throughout the Precambrian, and that your cherts are forming at this seawater sediment interface at the base of the seafloor, and that's where those circulation cells would be. And so it's a potential that this whole trend that we're reading into and trying to figure out ambient seawater temperatures, we're just reading the hydrothermal history of Earth, potentially.
Thank you.
Okay.